Because elements and compounds are so fundamental to the study of chemistry, it is useful to refer to them by symbols and formulas. Chemistry has its own language with symbols as letters, formulas as words, and chemical reactions as sentences. The chemical symbol is a one- or two-letter designation derived from the name of an element based on the English or Latin name. The first letter of the symbol is capitalized, and the second one is always lowercase. It makes a difference. If you write C small o versus C capital O, that makes a major difference. C small o is the chemical symbol for cobalt, while C capital O is the molecule carbon monoxide. So it makes a real big difference how you write the formula. Compounds are designated by combinations of chemical symbols called a formula. For example, the carbon monoxide we just referred to. Capital C and capital O takes two chemical symbols together, making a formula, carbon monoxide. If more than one atom is to be indicated in a formula, a subscript number is used after the symbol. So carbon monoxide, CO, has one carbon atom and one oxygen, while carbon tetrachloride has one carbon atom and 4 chlorine atoms. Note you should learn the names and symbols of all the elements. Let's talk about measurement and significant figures. Measurement is a comparison of a physical quantity to be measured with a unit of measurement, that is, with a fixed standard of measurement. It is important to give the unit of measure as well as numeric value. You should write like 9.12 centimeters, not just 9.12. The number in the units are important because it tells you which unit of measurement you're comparing to. If you measure something, you don't always get exactly the same number every time. There's some random error. Which gets us to the term precision. The term precision refers to the closeness of a set of values obtained from identical measurements of a quantity. In other words, it's reproducibility. How close are the results to each other? Accuracy, on the other hand, refers to the closeness of a single measurement to its true value. Basically, it's truthfulness of the data. How close is it to the actual value? So the question comes up, is it possible to have precision but be inaccurate? The answer is yes. You may have a systematic error causing all results to be off by a similar amount. Just because you're precise, it does not mean you're inaccurate. Basically, you can have measurements that are all about the same and still not be correct. Demonstrate this in a little bullseye. Okay, if you have a bullseye and you shoot your gun and you get all your targets in the same little area, well, the goal of it to be accurate is to get in the middle of that bullseye. Well, in this particular case, you can see the bullets were very precise, but they were not accurate. None of them hit the actual middle of the target. To indicate the precision of a measured number, or the result of calculations on measured numbers, we often use the concept of significant figures. Significant figures are those digits in a measured number, or the result of a calculation with a measured number, that include all your certain digits plus a final one having some uncertainty. Basically, the first digit that you're guessing at is where you stop on your significant figures. Take, for instance, this graduated cylinder. We can see we have divisions on the 1 milliliter and the 2 milliliter, and we have this meniscus somewhere in between the two. This measuring device has divisions up to the ones place. Therefore, the first uncertainty value, the one I'm guessing at, is the tens place. We are certain that it is greater than 1, but less than 2 milliliters. In this particular case, you can see it's about halfway between it, so we would call this 1.5 milliliters. Notice I cannot call it 1.5 something. I cannot go to the hundredths place because I'm already guessing at the tens place. So that is my first one that I'm basically guessing at, so that's where I have to stop with this measuring device. Let's look at another example. Let's look at a ruler in centimeters. We can see in this particular measurement that we know it is greater than 30 and less than 31 centimeters, but we need to figure out what are these little divisions. We can see that our divisions are in tenths. This is 30.1, 30.2, 30.3, etc., all the way to 31.0. So we know that this line is somewhere between 30.2 and 30.3. So we're going to end up guessing somewhere between those two where that ends. And since we know the divisions are to the tens place, we will be guessing at the hundredths place. Measuring device has divisions up to the tens place, therefore the first uncertainty value, that place I'm guessing, is at the hundredths place. We're certain it is greater than 30.2 but less than 30.3. So we will call this 30.22 centimeters. Now you may call it 2.3, somebody else may call it 2.4, it doesn't matter. That last digit is that uncertainty one, that we're guessing at. Since the last digit is uncertain, it doesn't matter which one you pick. Let's look at the rules for significant figures. These are things that you must learn and follow. You'll be using this in every calculation you do. The first rule is all non-zero digits are significant. Look at example 111. You see that we have 3 non-zero digits. That means that all 3 of those ones are significant. 1,286, all those are non-zero digits. Therefore, all 4 of those are significant as well. Second rule, zeros between significant figures are significant. We have 1,001. The 2 ones are significant because there are non-zero digits. That makes those zeros in between significant because they are between 2 significant digits. 20,006. Once again, we have 2 non-zero digits which are significant, the 2 and the 6. That makes all 3 of the zeros in between significant. Therefore, for 1,001 we have 4 significant figures. For 20,006 we have 5. Rule 3, which is a very important rule. A lot of people forget this rule. Zeros preceding the first non-zero digit are not significant. Until you reach the first non-zero digit, you have the zeros are insignificant. Example, 0.002. All those zeros before that 2 are just set in the decimal place, so none of those are significant. Therefore, there is only one significant digit in 0.002. Let's look at 0.00206. We know that the 2 and the 6 are significant from rule number 1. They're non-zero digits. We know that that 0 in between the 2 and the 6 are significant because they're between non-zero digits. However, those first 3 zeros are only set in the decimal place, so they are not significant. So therefore, the first one, 0.0002, has 1 significant figure, and 0.00206 has 3 significant figures. Zeros to the right of a decimal after a non-zero digit are significant. So if we're talking about zeros are to the right of a non-zero digit, okay, and are to the right of the decimal, they are significant. Examples. First one, 0.00300. Well, the first three zeros we know are not significant because they were preceding the first non-zero digit. We know the 3 is significant by rule number 1. And then now we have these last two zeros which are significant based on this rule. Because they are to the right of a non-zero digit and they are to the right of the decimal, they are significant. So therefore we have 3 significant figures. Let's look at the second one, 9.00. We know the 9 is significant. Now we have these zeros to the right of that non-zero digit and then to the right of the decimal. Therefore we know that those are significant. So all 3 are significant. 9.10. 9 and 1 we know are significant due to the fact that they are non-zero digits. We have a 0 that is after a non-zero digit to the right of it and also to the right of the decimal. Therefore all 3 of those are significant. 90.0. Well, we know the 9 is significant because it's a non-zero digit. Now based on this rule, the 0 is to the right of a non-zero digit and to the right of the decimal. That makes this second 0 significant. And now we know that this 0 now, the one in between, the purple one, is in between 2 significant digits, therefore it's significant as well. Therefore all 3 of these digits are significant. So for the first one, 300 is significant, so you get 3 significant figures. The second one, 9.00, all 3 are significant. 9.10, all 3 are significant, as well as for 90.0, all 3 are significant. Zeros at the end of a non-decimal number may or may not be significant. We tend to use scientific notation to indicate significant figures in those digits that we're trying to indicate that are significant or not. Example, 900. Well, for 900, that could be 1 significant digit, could be 2, could be 3. We don't know what's going on with those last 2 zeros. Sometimes we put a decimal after it to indicate that all 3 are significant. So 900 could be 1, 2, or 3 significant figures. So how do we get around that? We use scientific notation. Scientific notation is a representation of a number in the form of a decimal times 10 to the n. That decimal is after that first number, where a is a number, significant digits only, with a single non-zero digit to the left of the decimal point, and n is an integer or whole number. Now we can have notation where we have several numbers before the decimal place, but that's just put it in notation. To call it scientific notation, it is one number, then the decimal, and then the rest of the numbers that are significant. Let's go back to that 900 number. We know that there's a decimal technically behind that last 0. Okay, it may or may not be there. Now, we may want to represent this as 1, 2, or 3 significant figures. We may want to put this in scientific notation to tell the individual how many sig figs are actually there. But first we need to figure out what is that power of 10. What is that n value for that power of 10 while we're writing the scientific notation. If you move the decimal place to the left until you have a single non-zero digit to the left of the decimal place, n will be a positive integer, equal to the number of decimal places moved. In this case, the decimal is moving 2 decimal places. It's going to move from its location here to get to this point. It's going to gain 2 decimal places to move it, and it'd be a power of 10 to the 2. We may write that 900 as 1, 2, or 3 significant figures by using scientific notation to indicate that number. So this 900 number could be written one of several ways. We could write it as 9 times 10 to the second, which is basically still 900, but it's indicating that only that 9 is significant. We could write it as 9.0 times 10 to the second, which is indicating that it's two significant figures, the 9 and the first 0. But it still represents the same numeric number, 900. You must put that time 10 to the second to indicate that it's 900. Or we could write it as three significant figures, 9.00 times 10 to the second, indicating that all three numbers are significant. Let's look at 300 million. Now, this could be many different significant figures, but I'm going to, in this particular example, choose to make it three significant figures. Once again, we're going to have to figure out what is the power of 10, so we're going to have to move the decimal place all the way over till we get to that point after the first one. The decimal is moving 8 decimal places, making n equal to 8. And arbitrarily, I've selected to make this 3 sig figs in my final answer. So the final answer would be 3.00 times 10 to the 8th. That is equivalent to 300 million with 3 significant figures. Now let's look at what happens going the other way. Say I have a decimal number and I want to put it in scientific notation. Well, in this particular case, we're moving the decimal to the right, so we are losing decimal places. If you move the decimal place to the right until you have a single non-zero digit to the left of the decimal place, n will be a negative integer equal to the number of decimal places moved. In this case, the decimal is moving 5 decimal places, so n is equal to a negative 5. So I write this number as 3.01 times 10 to the negative 5th, indicating 3 significant figures. Remember, those first decimal places are just, the first zeros are only marking the decimal place. Let's look at 843.4. Let's write that in scientific notation. So what I'm going to have to do now is take this decimal and move it to make it that one digit with the decimal behind it. If I do that, we can see that I will gain 2 decimal places, moving it to the left. And all these numbers are significant. So therefore, my result would be 8.434 times 10 to the second. Let's look at the next number, 0.00421. This is a decimal number, so this is one I'm going to have to move the decimal to the right, and I'll be losing decimals. So in this case, you can see I'm going to have to move my decimal 1, 2, 3 spots. Once again, looking at significant figures, this is only going to have 3, 4, 2, 1. The zeros in the front are not significant. So that makes it 4.21 times 10 to the negative third. 6.39 times 10 to the negative fourth. Trying to write this one in regular numeric number, that means I got to take this decimal place now and move it 4 decimal places over, which means I will have 3 zeros in front of that 6, which now means I have 0.000639. Notice what we did was we took the decimal place right here and moved it 4 decimal places, and that's how we figured out that we had 3 zeros in the front. Let's take 3.275 times 10 to the second and write that in regular numeric number. Means I'm going to take that decimal, move it 2 decimals to the right, and the number will be 327.5. Homework 2 and 3, you should be able to handle these following these rules of significant digits.